Okay, so I want to look at vertical motion. Now we've already done a little bit of this sort of thing when we introduced ourselves to conservation energy and potential and kinetic energy. You can go back to page 95 of your textbook and exercise 5b, and we're going to revise on some of that, those ideas. So in terms of vertical motion, the most obvious one is the pendulum, which I'm showing you here, and I'll talk about that in a moment. There are other ones, and we'll get onto those in due course. So basically, imagine if you had I suppose a ball inside a cylinder, and it was just oscillating, or it was spinning around, or if you had like a daredevil wanted to do the loop inside effectively a cylinder. How would they do that? What speed they have to be going at? We can also look at the scenario where you've got something on top of a cylinder. So you imagine a cylinder and you have an object on top of it, and you let go of it, a marble or something, and it'll slide or roll down the side of that cylinder, and at some point in time it will lose contact with that cylinder, circular sort of face, and fall off out. So we're going to look at a few of those different scenarios. Okay. So I've slowed this pendulum down, and we're going to have a little look and see what's going on with it. So you can see there is the black line is a string, and it is taut, and there's an object on the end of it, and it has a mass, and because of gravity, there is a force going down, vertically down, mg. It's labelled there F gravity. So whatever the mass is, m multiplied by g would be that force acting down. Okay, well that's not the only force that's acting. So what else have we got? Well, we've got a tension on the string, and you can see that by virtue of the red arrow. So that tension you can see is getting greater, and then it's getting less, and then it's increasing, and it's getting less, and so forth and so on. So you can see there's some movement on that in terms of that tension. And then if we appreciate, for example, that gravity has sort of several components to it, so we can look at the gravity in terms of the tangential force from the gravity, and then also the force in the sort of radial, so in direction of the radius or the center. So if we look at that F radical, that is the part of the component of the gravity that is acting in direction of the center, and that the tension on the string and the force from the gravity in the direction of the string of the center is what's going to create the centripetal force. So you can appreciate the blue arrow there is the total centripetal force. Okay, and there's also a graphic at the top there where you can see the various different components, the tension increasing and decreasing, the amount of the gravity that is acting in direction of the center of the circle, and then the blue line is basically the sum of those two. If I also show there the velocity of the object, so the tangential velocity, you can see there like a light blue arrow, and it's showing the velocity it's sort of speeding up, slowing down, and the other direction, speeding up and slowing down. And you should know at this stage, if you're fairly familiar with the idea of the pendulum, it speeds up, it slows down to its velocity 0, at which point it stays stationary momentarily, and it speeds up in the other direction, and then slows down, speeds up, goes to the center, and it's at its maximum speed at that bottom point. Okay, so what else have we got going on here? Well, what I could point out to you might have noticed already at the side here, we've got two other sort of graphics here, KE and PE. So KE is for kinetic energy and PE is for potential energy. And then we've got the sum total of the energy. And the sum total of the energy does not change. So there's a conservation of energy. The energy stays within the system, but it's just transferring, and that mechanical energy, for one of it, that sum total can be broken down into kinetic energy and potential energy. And when it is moving, it has kinetic energy, and we can measure, I suppose, the change in potential energy. You can define your sort of 0 point wherever you like. So for this purpose, we'll consider it to be at that lowest point in the circular motion. PE is 0 because the height from that, you see the grey line there. Okay, that grey line there. Okay, is that point, the height from that point. So let's just stop it for a second. So that when we got that certain height there, that height, so mgh is potential energy. So mass multiplied by gravity multiplied by the height gives you a measurement of the potential energy. It starts again. So when the height is 0, that's when the potential energy is 0. Meanwhile, for the kinetic energy, when it's momentarily stationary at either end of its movement, the kinetic energy is 0. So let's just see if we can pause it just as it gets to that point. Okay, so at that moment in time, it's basically stationary. That V is almost 0, and the kinetic energy is 0. And kinetic energy is measured at half mv squared. So the kinetic energy is almost 0 when the velocity is almost 0. And it'll be at its greatest when it is at that bottom point. Its velocity is maximized. All the potential energy has been transferred into kinetic energy. And so you have a full, let's see if we can pause it there. At that moment there, you've got full kinetic energy and no potential energy. So if we add the two together, so mgh plus a half mv squared, that's your standard formula to describe the sum of the two energies that we're interested in. And you can take two separate points in time, and the energy, total energy at one point must be the same, equal to the energy at another point. So we're going to look at a few questions where we're revising our understanding of that and using it, and then we'll bring in the issue of the tensions and so forth, and how we can link the conservation of energy with the sort of looking at the sum total centripetal force. Okay. And just very quickly, before we go on to that, just a few other scenarios. Let's just get this going, and let's just change some of the scenarios. Let's speed up. So let's, at the bottom point here, let's have a greater speed. What will we have as a result? So the pendulum, if it has a greater speed when it's sort of set off, it's going to have a bigger swing, I suppose. And this is how you know from just as a kid playing with swings, you need a faster speed in order to get your swing to go up higher. Okay, and if you're pushing the kid, then it's more force to try and get the child, the swing sped up to the point where it can actually reach the high levels. Right, anyway, so that's fine. I don't know why this thing is strange. Okay, so G is 9.8. I don't know why you can change G, but anyway, when I reset it, it goes to 10, which is a bit stupid. Anyway, so let's just change the speed of it. Okay, so that's its initial speed is 6.5, and you can see there it's actually doing a full circle. Okay, the tension is kept. So if you remind yourselves, the tension was the big red arrow that's pointing towards the middle. That tension there, that top red arrow there, is always there. It's never 0 or negative as such, and the whole system is carrying on. Now it speeds up, and then it slows down again, That's still got that transfer of kinetic energy and potential energy. Now, because it's moving, it's carrying on moving at that point at the top there, it still has some potential energy. Okay. And we can look at scenarios where we sort of get to the point where it only just gets to the top before it starts falling down again. Let me just see if I can just about get it to a bit more. Let's see if I can. So it slows down. That V is really slowing down. It's still quite difficult to actually to set it up. But anyway, right. So let me just. Oh, it's doing weird things now. Right. Okay. What if it didn't have quite enough speed? What's going to happen? Well, you can see there what happens is the tension is lost. So not quite enough speed when it's set off. Doesn't quite get to the top, and the system fails. And the reason for that is it's to do with the forces that are acting. So you're going to see here that the tension gets to the point where it gets to zero. Once that tension is zero, the whole system fails. And we'll sort of discuss a little bit about that. Okay. So right, without further ado, let me do a few questions. Let's start off with a fairly easy question, and this one is just going to be looking at revising our ideas about using kinetic energy and potential energy. So, a small particle of mass 1 kg is attached to the end of a light and extensible string of length 0.5. That's the radius, I suppose, of the circular motion. The other end of the string is attached to the ceiling. The particle is drawn aside so that the string makes an angle of alpha, where tan of alpha is 3/4. With the downward vertical as shown. Okay, so the alpha is that, so the string and the downward vertical, that angle difference is alpha. If the particle is then released, find its maximum speed in the subsequent motion. So we're allowed to just know that it's going to have that maximum speed when it's doing that circular motion at that point in time at the bottom. Okay, so we can sort of say point A and point B, and when it goes from point A to point B, when it gets to point B, it's going at its maximum velocity. What can we understand? Well, we need to appreciate the system here. From, if we call that point the fixture at the top there, if we think of OB and OA are both a half, okay, so the distance from O to B is a half, then we can appreciate that. Just draw a line from O to B, and let's draw a horizontal line from A. So that radius is broken down into two separate parts, and we can talk about the that didn't really work, did it? Didn't quite get it in the right position, but anyway, can I move it so it's in the right position? Yes, I can. Yes, we can. I feel like I'm. So the key thing is, and I might redraw this, the key thing here we've got a difference in the height. Okay, so that difference in the height there, okay, that's what we're going to call H. So how can we describe H? Well, let's think about the triangle that we've got going on here. So let's draw a bigger diagram, slightly not to scale. So we're going to call that H. That's 0.5. This total distance is 0.5. So we can describe this section here up to O. How can we do that? Well, if we think about a right-angled triangle, we've got our adjacent and hypotenuse. We've got cosine, and we're wanting the adjacent, so the adjacent is going to be equal to the cosine of the angle multiplied by h. So 0.5 lots of cos alpha. Okay, now if we appreciate that the tan of alpha is 3/4, alarm bells should immediately ring, and you should realize it's 3-4-5 triangle, and the cosine of the angle is going to be 4/5, and the sine of the angle is going to be 3/5. So we can straight away say that that's 0.5 multiplied by 4/5, which gives me an answer of 0.4. Okay, so we can appreciate that's 0.4, and therefore this total distance here, it's going to be 0.1 then. Okay, so a little bit of trigonometry there, just appreciating how high it's getting to. They've given us the angle, so it is a specified height, and we've been able to find it out. Okay, so we know that height is 0.1. So, okay, well, let's think about the two different positions, the position at A and the position at B. So at A, that top position, okay, so at point A, we're going to have a situation where it's stationary, okay. The idea is just release from that point, okay. So the kinetic energy is 0, and the potential energy is going to be mgh. And the mass is 1, gravity is gravity, and the height that it is from the baseline, I suppose, is 0.1. So we've got 0.1 g. Energy is measured in joules. Okay. At the bottom, at point B, we've got a situation where the potential energy is 0. And the reason for that is h is 0 at that point in time. Okay, so mg 0, so mg multiplied by 0, and m is 1, but the point is it's 0. The kinetic energy is a half mv squared. We don't know what v is, we know what m is. So we're getting a potential energy of half v squared. Okay, so if we remind ourselves, conservation of energy, that the KE before and the PE before added together is going to equal the KE afterwards and the PE afterwards. I suppose we could have said A and B, couldn't I? Anyway, so, and I've written all this out. In reality, you'll probably do a lot of that in your head. You'd straight away write out your equation for the conservation of energy, and straight away you'd be saying, okay, so a half mv squared. Okay, and you'd straight away put it in. But I'll tell you what we'll do. We'll just formally write that out, that formula. So it is a half m v1 squared plus, let's take that, sorry, mgh, and then it's a half mv2 squared plus mgh2. So whatever the heights are, whatever the velocities are at one point, and whatever the velocities and heights at the other point, you can put them into that basic formula. So that's what I've been doing, sort of piecemeal, each individual part. Anyway, so the kinetic energy is 0 initially, and the potential energy is 0.1 g, or 1/10 of g, and the kinetic energy afterwards is a half v squared plus potential energy of 0. So we end up with, I suppose, v squared equaling 0.2 g, and if we get a calculator out, well, so that's g over 5, isn't it, being square rooted, and I get an answer of square root of 9.8, That's what G is divided by 5. All square rooted is 1.4. So I know then, meters per second, I know that its velocity at that lowest point, the greatest velocity, is going to be 1.4 meters squared. Okay, so moving on to another pendulum style question. A particle of mass m is suspended with a light inextensible string of length 1 meter. The particle is suspended at rest with the string vertical. So it's hanging down, basically, is what it's saying. Okay, it's going to left hanging down at rest. Okay, the particle is then given a horizontal velocity of 6 meters per second. So it's fired from that sort of vertically down resting point at a velocity of 6 meters per second square, 6 meters per second. Find the angle the string makes with the upward vertical at the instant when the string goes slack. So it's suggesting that the pendulum is going to go above the horizontal. So if you think about it, the string can be horizontal at that sort of the far reaches of that pendulum style, but it's going to carry on up. Okay, and then it's going to go slack. It's not going to be able to get all the way up and back around. Okay, so let's set ourselves up and see what we can describe in terms of the energy, and then separately to that the tensions, the forces. So that's our two scenarios: the string hanging down, and there's tension on the string, and there's gravity is creating a weight to the object, and then when it's swung all the way around, okay, it's got to another point, and there the angle we're describing is the angle with the upward vertical, as it asks. And what have we got in terms of we've got the weight vertically down. We've got tension on the string, which is still just about taut. Okay, so when the string goes slack, so we're interested in that moment just between it going slack and it being taut. Okay, so what is going on in terms of this system? Well, probably the first thing we need to do is appreciate the energies that are occurring, and then second to that, we'll then look at hopefully we'll make a link in terms of velocities and the heights with being able to look at the tensions. So let's look at the distances we've got going on in terms of this triangle here. We've got 1 cos alpha is that vertical distance. So the total height of the object above. Okay, so we're not including that bit there. So we're looking at the height that has traveled upwards. What is that going to be? Well, it's going to be 1 plus the cos of alpha. Okay, in total. So let's look at the potential energy and kinetic energy beforehand, or at the moment it starts, the bottom. So at the bottom, we don't know what the mass is. Maybe that's not important. The velocity we're told is 6 initially. Now the height at the bottom is 0. Now at the top, okay, so we don't actually know that velocity that it's actually traveling at the top. And the height is 1 plus the cos of alpha. Okay, just inside the screen there. So on the left hand side, I'm going to get a half of 36 multiplied by its mass, and on the right hand side, I'm just going to get a half mv squared plus mg1 plus the cosine of alpha. Okay, I can rearrange that. I suppose it might be easy if I double everything and bring everything to v and divide everything by m. So if I double everything and I divide by m, I'm going to end up with 36 v squared and 2g 1 plus cos of alpha. I'll bring that on the other side. I end up with 36 minus 2g. Now I'm not quite sure when I want to actually open up this bracket here. Let's keep it as it is for the moment. You might find it's useful to open it up at some point in time. Anyway, I've got an expression for the velocity at that moment in time. So what we're talking about here is the velocity that it's going at technically at that moment in time. It is still going, it's tangential velocity, but at some point in time we're going to talk about this idea that, okay, at that angle of alpha, that's the moment in time when it stops doing circular motion. So I've just rewritten the diagram that we see here. Okay, and I've just drawn it a little bit bigger. We've got centripetal acceleration at that moment in time, up until that moment in time, and we've got gravity acting, and technically we have a tension acting in the direction of the center of the circular motion. What's the component of the gravity that's acting in that direction? Well, we can draw ourselves a little right angle triangle, and we can appreciate that now the angle is alpha. If you think about alternate angles, you've got the Z rule there. If that's alpha there, then this angle in here is alpha. And the component of the gravity that's acting in the direction, the same direction of the tension, it's going to be mg cos alpha, because again, it's the adjacent part of that diagram. Okay, the angle is here, and it's the adjacent part. Okay, so we have our total sort of forces acting is going to be the tension, and we're adding on to that mg cos alpha. Okay, that's the total force that's acting on the object, and we can see it's the centripetal force. The centripetal force can be described as being using F equals ma, where a is v squared divided by r. We got the centripetal force is equal to mv squared over r. Now, at the moment that the string goes slack, okay, T is equal to naught. So it's really important to appreciate the idea of, okay, when it's slack, okay, basically tension is 0. Okay, so in this instance, we're going to have to, we just have the idea that as a result, mg cos alpha is equal to mv squared over r. Okay, so just the idea that the tension is 0. Okay, so let's investigate that, and then we can use an expression for v squared in that formula. So let's explore that. So we've got mg cos alpha is equal to m multiplied by the velocity. So we've already worked out at that moment in time the velocity is velocity squared, is 36 minus 2g brackets 1 plus cos alpha. Just want at one point in time I'm going to open up that bracket, and that's all divided by the radius, which in this instance happens to be 1. It makes life a little bit easier. Now m is a factor on both sides, so I end up with g cos alpha is equal to 36 minus 2g minus 2g cos alpha. I'm trying to isolate the cos alpha to some extent, so that's why I'm now starting to open this up. So 36 minus 2g, g is 9.8, 2 lots of g is going to be 19.6. Taking that away from 36, I end up with, let's just get this right, so I'll keep that g in for the moment. Okay, cos alpha, 36 minus 2g is 16.4. I've still got 2g cos alpha here, so hang on a second, I've got g cos alpha on this side, I've got minus 2g cos alpha on the right hand side, so bring those together, I get 3g cos alpha, leaves 16.4, and therefore, if I divide by 3g and do the inverse cosine, I'm going to end up with an angle of, let me get my calculator out, I get 56.09, so let's just call it 56.1 degrees. Correct to one decimal place. So that's the angle that it gets to with the vertical, at which point in time the circular motion ends. The tension, it's not going fast enough basically, so it can't manage to get itself all the way up to the top. Okay, the tension disappears in the string, and it sort of becomes a projectile basically. Now there's various different sorts of questions in exercise 7D that you can be looking at, which are similar to this, involving some sort of pendulum. Questions 1, 4, 6, 7, 8, 10 and 13. I will do some more questions looking at other scenarios in a separate video. I've been yabbering on long enough, half an hour. Okay.